multiple alleles. Do you need the colors after the number? No, so Abby, the reason I included the colors is just so you understand which numbers I was doing. Like in the homework assignment, people would do like too tall to too short. So it just kind of helps you realize that you have to write the dominant before the recessive. Yeah, so Mr. Monzon saying you should add the colors, yeah, for clarity. So you know what the numbers represent. Okay, multiple alleles. So when we're talking about multiple alleles, what we mean here is that you always get two alleles for every trait. Okay, you get one from mom and one from dad. Okay, that has not changed. You still only get two alleles for blood type, which is our multiple alleles example. But why it's called multiple alleles is because there are three possible alleles out there in the human population. Okay, so instead of there just being two, dominant or recessive, there are three possible alleles out in the human population. And it's because of this, blood type is unique. So when you have another part of it that's unique is that when you have type A and type B blood alleles together, they're actually co-dominant. So this is also, in addition to being multiple alleles, if you're looking at the AB blood type, it's also co-dominant. And the co-dominant part has to do with the type of antibodies and antigens that we have on our blood cells and why you can only receive certain types of blood. So I have a chart here that kind of goes through this. And if you have, I'm going to go over pretty quickly because I'm more going to talk about how you get your blood type. And if you have further interest in this, there's a link here you can go to learn more about blood types. So if you are type A blood, your blood cells have what we call an antigen, which is a marker on your blood cells that tell your body that A blood is safe. That's a part of your body. And in your blood plasma, you have what's called an antibody for B, which means your body will attack a blood cell that has a B antigen on it. Okay, so if a type A blood person were to get B blood, these antibodies would attack a B blood cell and destroy it. The immune system would see it as a foreign invader and it would destroy it. Type B blood has B antigens on it. And type B blood has antibodies for A. So if a type B blood person got A blood, it would destroy it. Okay. Now, AB, this is where the co-dominant part comes. AB blood cells have both B and A antigens on them, and they don't have any antibodies in their plasma. What that means is AB blood people, they can get blood from any type of blood. Their body won't reject it. Type O is the fourth type of blood. And type O has no antigens on their blood cells. However, type O people have antibodies for A and B. So if you tried to give A blood to O, they would destroy it. If you tried to give B blood to O, they would destroy it. If you tried to give AB blood to O, they would destroy it. Okay, so this is what we mean by this is the co-dominant part of this. By the way, so type O can donate to anyone, but type O has to get blood from only type O blood. All right, so again, I'm not gonna go into much more detail than that, but if you are interested in learning more about blood types, there's that link there. Angelina, I don't know what golden blood is even, so. Type O is actually the most common, the most common blood. AB is the rarest blood. All right, so let's talk about those multiple alleles with their superscripts. So a superscript is when you write a letter up in the upper right-hand corner of another letter. Okay, so there are 3 possible alleles in the human population, like I said. You can have the dominant A allele, and we write it with an uppercase I and a superscript with a dominant uppercase A. You can have a dominant allele with the superscript B, or you can have the recessive allele written with a lowercase I. So these are uppercase I's representing the 2 dominant alleles, and then the lowercase I is the recessive allele. So again, I is recessive, and the dominant A and dominant B are co-dominant when they're found together. And this is why there's 4 different blood types, okay? Because there are 3 different alleles in the human population, that's why there are 4 different blood types. So we're gonna look at how you get each blood type down here, but I just wanna remind you, when you do blood type Punnett squares, you must include the I, whether it's the uppercase or the lowercase. If it's the uppercase, you must include the superscript. And then if it's the lowercase I, there's no superscript. There's no letter on the recessive allele, okay? So let's take a look at how somebody could be type A blood. So the phenotype is type A blood. The genotype, there's actually 2 possible genotypes for type A blood. So you could be homozygous for A. So you could be homozygous dominant for A, having 2 of the same A alleles. Or you can be heterozygous for A. You can have 1 dominant A allele and 1 recessive allele. And you're still A. The same thing goes for B, except for you could be homozygous for B, have 2 dominant B alleles, or you can be heterozygous for B and have 1 dominant and 1 recessive allele. Now, AB blood and type O blood only have 1 genotype. So AB blood is when you have 1 of each of the dominant alleles. So you have 1A and 1B. And type O blood is the homozygous recessive blood. By the way, I am type O blood, so I am homozygous recessive, and my dad was type A blood, and my mom was also type A. So I know that my mom and dad both had to be heterozygous because they both gave me a little I and made me have type O blood. So let's work right now at setting up a Punnett square with blood type. Most of the rules that you've learned so far and that you feel comfortable with still apply. It's just that now we must include the superscript, otherwise we're not doing it right. Okay, so here's my parents, not my parents, but here are 2 parents. One has type A blood and one is type B blood. So just like before, when these 2 parents make gametes, those 2 alleles are gonna separate. Okay, but now we just include their superscript along with their dominant or recessive allele. Okay, so we're gonna put 1 parent, I'm gonna put the type A parent on the side here. Again, it doesn't matter where you put them. You can put the type A parent on the top if you want. And then this type B blood dad, I'm going to say it's dad, is going to give little I or the dominant B when he makes his sperm. So I'm going to put those on the top. All right, so now we just fill in our Punnett square over here. When you fill it in, you must include the I with the superscript, if there is one. Also, if you have both A and B, you always write the A first. Okay, so when you fill in this square, you always write the A before B. And that's because it's called AB blood, not BA blood. Even though AB blood is pretty BA. What did I just say? I don't even know. All right. So 2 of the babies are going to be AB blood. And these 2 babies are going to have a different blood type.
Fun.
Yeah. So these 2 parents being type A and type B, they have an opportunity to make a baby that has blood that neither one of them even has. So this is pretty unique. So what is the chance that the offspring are going to have type A blood? This is percent chance. Ooh, be careful. You might need to check your our chart up here again to see if any of the babies will be type A. Yeah, so I'm seeing 50%. So there would be this square is a type A and this square is a type A, right? So this might take a little bit of looking at a key to make sure that you understand the type A and the type AB and all those. So it would be 50%. And that's referring to these 2 babies over here, right? Those would be type A. All right, what percent then would have AB blood? Also 50%. Could these 2 parents have a type O baby? Nope, they sure can't. Because in order to have a type O baby, both parents would have to have a recessive allele to give to their baby. So no way, these 2 could not have a type O baby. So it's just, this is really similar to what you've been doing. It's just you have to include the letter I with its superscript or the recessive I. Wouldn't IB go first, the IA? So when we write this, because we call this AB blood, and because both of these are dominant, we usually write the A before the B in the genotype. And you see that up here as well in this chart. Okay, so let's do another one. Let's cross a parent who is AB blood with type O blood. So these are our 2 parents. We're going to separate their alleles. Remember, you need to include the I with the superscript if it has one. It doesn't matter what side you put which parent, as long as you keep their alleles together. And then you're going to write the dominant allele first. I'm going to make this bigger. And the recessive second. All right. And then once you have your Punnett square filled in, you can start answering some of these questions about it. So what percent of the offspring will have type A blood? Yep, it's 50% again. So it's these babies on the left over here for on my Punnett square. Might be in a different place if you put the parents in a different size. And then what percent of the offspring will have a heterozygous genotype of any kind? Yep, 100%. Good. So you're recognizing that all of these babies are heterozygous. Some of them are heterozygous for B blood and some of them are heterozygous for A blood, but they are all heterozygous. All right, and that's it. That's it for blood type multiple alleles. So the big thing is you must remember to always use the uppercase I and the superscript or the recessive little I when you're filling in the Punnett square. Okay, so you have to include both. Otherwise, you're going to start thinking you don't know what's going on. This is my superscript. That's his cape. That's a superscript cape on there. All right, so we're going to move on now to look at the next type of inheritance pattern that falls on the X chromosome only. Okay, so we got to remember a couple things about what the X chromosome is. So I'm going to remind you that you have 23 pairs of chromosomes. Your 23rd pair of chromosomes is called your sex chromosomes. And if you are a female, you have XX, 2 X chromosomes. And if you're a male, you have XY chromosomes. You only have 1 X. So we're talking about inheritance patterns today that fall on the X chromosome only. Okay, so we're also going to be focusing only on X-linked recessive traits. So some examples of X-linked recessive traits are color blindness, where you can't see colors quite the same as somebody that's normal, has normal vision for color, and hemophilia, which is a disease that doesn't allow you to clot your blood as well. So it leads to people bleeding to death. And especially back in the day when medicine was less sophisticated, people that had hemophilia died at a young age usually from bleeding. Nowadays, if you have hemophilia, they can give you medication to help your blood clot, and there's other treatments that they can give you, like plasma donation and stuff like that. But hemophilia is a pretty, like color blindness, while it might be inconvenient, is not fatal. Hemophilia could be considered fatal if you can't clot your blood. It could lead to death. So these traits for color blindness and hemophilia reside on the X chromosome only. Okay, so males only have 1 X, so they can inherit the disorder on their 1 X chromosome. So if they have just one of the recessive alleles on their X, then they have the disorder. Okay, they only have 1 chance of getting, if they get the recessive allele, then they're going to have the disorder, like something like color blindness or hemophilia. Females, on the other hand, need to have the disorder on both of their X's. So in order for them to have something like color blindness or hemophilia, they have to be homozygous recessive and have the recessive allele on both their X's. Now, these recessive alleles are not all that common, so it's not very common for a female to have 2 of them, but it is common and more likely for a male to have the 1 recessive allele, which is why more men are colorblind, and also why more men have had hemophilia in the past, especially back when they weren't able to do anything about it. So let's take a look at a little bit more information here. I've written a lot of this out for you. So if you are confused or you want to look back at this, you have all this information here. So there isn't anything on the Y chromosome. So males that are XY, the Y chromosome doesn't have these traits that we're going to be talking about today. And that's because the Y chromosome is shorter. It's even, if you see a picture of it, it's actually slightly shorter than the X. And the traits that we're talking about don't lie on the Y chromosome. So it's because males only have one X. If they get just one of those bad recessive alleles, then they have the disorder. Okay, so this is why so many males are colorblind. It's really rare to find a female that's colorblind. Because females have two X chromosomes, they can have one bad recessive allele and one good dominant one and be fine. But when they have the recessive allele on their X, we consider them carriers because they carry the recessive allele that can lead to color blindness or hemophilia. So they could later pass that on to their offspring, but their phenotype is that they're normal sighted and they don't have hemophilia. So they can be, as females, we can carry it and not show it. So as with blood type, when we are doing X-linked recessive Punnett squares, we must include the X and the Y, as well as the superscript again. Okay, so you have to include the X and Y and then the superscript on the X. There will be no superscript on the Y because it doesn't carry these traits. All right, oopsie, I meant to erase this earlier. Sorry, this was from last hour. You guys didn't see that. Okay, so before we start adding superscripts, I just want to do a quick Punnett square to show the chances of having a male or a female baby. Okay, so we're going to do this one first without any alleles. So what I have set up here is just a Punnett square showing the male, dad is on top with his sex chromosomes and mom is on the side. Okay. And you're just going to fill this in like normally you do just to see what are the chances of having a male or a female on any given time that a man and a woman have a baby. So if you fill it in, you'll see. Oops. Sorry. You always write X first. I'm not sure why, but you always write the X first. All right, so I wanted you to circle the females and put a box around the males. So we're going to circle our females. And put a box around the males. Oh, I love that. I love this about Notability too. It makes perfect squares and perfect circles for you. So who determines if the offspring is going to be a male? Which parent determines? Yeah, Abby, dad. And the reason for that is that dad is the one who gives his sons his Y. Okay, dad is going to give his sons the Y every time. If dad gives his X, then he's going to have a daughter. Mom, on the other hand, she can't give anything but an X. So for number 5, the only chromosome that mom can give her offspring is an X. So she gives the X or the X. Now, once we start putting alleles on them, she could give a dominant or a recessive if she has both. But we're just talking about the chances of having a male or a female at this point. And there's a typo in question number 6, because there's not only one chromosome that dad can give. What are the chromosomes that dad can give to his offspring? He can give X or Y. This is going to become more important when we start talking about pedigrees, because anytime a male has a son, he gives his Y to his son. He gives his X to his daughter and his Y to his son. And when we start talking about X-linked traits and disorders, you have to realize that dad gives his sons the Y always, and he gives his daughters his X. All right. Oh my gosh, I am so sorry. I forgot to erase all of this stuff here. So why don't you guys take a look at your next page while I erase my 4th hour work here. And I'm sorry that I didn't do this beforehand. All right, so we're going to look at color blindness first. And let's first look at possible genotypes and phenotypes for males. So I'm going to zoom in on my males over here. So males can have 2 possible genotypes. They can have a big B, the dominant B with their Y, and then they have normal vision. Or they can have the recessive allele on their X, and then they are colorblind. We have to include the X and the Y so we know what the sex is of the child. So XY means male, so either you have a big B and you're normal, or little b and you're colorblind. Males cannot be carriers, because the definition of a carrier is that you carry the recessive allele, but you don't have the disorder, and that's not possible with males. Okay, now let's scroll over to look at our females. So females can be homozygous dominant, so have 2 big B's on their X's, and then they are female normal vision. Females can be heterozygous, meaning they have 1 dominant X and 1 recessive X. Then they're female with normal vision. However, now we call them carriers, because they could pass this dangerous or colorblind, not really dangerous, allele onto their sons or their daughters, but they're not showing the trait in their phenotype. They have normal vision. And then the last genotype is little b, homozygous recessive. That is a female who is colorblind. All right, so we are going to cross a normal visioned male with a female carrier. Okay, so this is giving you enough information to write down the genotypes of the parents. So normal vision male, if you just look up here, is dad has a big B and a Y. And a female carrier is an X with a big B and an X with a little b. You must include the X and the Y and the superscript on the X chromosome. All right, and then I set up all these Punnett squares with the X and the Y already for you, because I just want to make sure that you're using the X and the Y. So you just need to add the superscripts. I've done part of the work for you. So dad is normal, mom is a carrier. All right, now just like the blood type examples, you must include the X's in your Punnett squares, just like you included the I's. So when you write your genotypes of the babies, you must include the X's and the Y's along with their letters. And dominant still always goes in front of recessive. All right, so once you have them filled in, you can start answering questions about them. Now, the way that I have these questions written, I'm asking what are the percent chances of them having any of these possibilities. So if I said, what are the percent chances of them having a son with color blindness? We're just looking for the square that would have a son with color blindness. So what is the percent chance?
50%.
It's not 50. We're looking for a son with color blindness. This son up here does not have color blindness. Yep, so 25%. So Lorelai, you were right that they have a 50% chance of having a son, but they have a 25% chance of having a son who is also colorblind. If I said what percent of their sons would have color blindness, then you would have been correct with 50%. So does that make sense? If I said of their sons, what percent chance do they have of having color blindness? That would be 50% of their sons.
Yeah, I didn't look closely enough at the superscript.
Okay, that's all right. All right, what is the percent chance of them having a daughter with color blindness?
0.
That would be 0. How about having a daughter who's a carrier?
1 to 5.
Yep, so just like mom, this daughter right here would be a carrier. Oops, 25. I'm writing down the genotype. All right, for the next one, you're going to cross a colorblind female with a normal visioned male. So I would like you to try to do this one on your own first. So I'm going to give you a few moments here and see if you can figure it out. You're probably going to need to use the genotype list at the top and figure out what the parents' genotypes are first. All right. So if mom is colorblind, she is homozygous recessive. So both of her X's have the dangerous recessive little b. So what is their chance of having a son with color blindness?
Now it's 50.
It is 50%. It's the same percent chance of even having a son, right? So all of her sons are going to be colorblind, right? So if this couple has a son, 100% of their sons will be colorblind. And that's what we see when you have a mother who has a X-linked recessive trait, all of her sons have it because she has to give them the bad X. If she has it, she's passing it on to all of her sons. How about, do they have a chance of having a daughter with color blindness?
No.
They do not. What about having a daughter who's a carrier? That is also 50%. So it's the same percentage of having a daughter, right? So 100% of their daughters will be carriers. And 100% of their sons will be colorblind. All right, so that's all I have for you today. Your homework is going to be to do a couple examples of X-linked traits. So you're first looking at fruit flies, where eye color is X-linked recessive. So red eyes are dominant to white. So the same thing goes as it just did in your notes for color blindness, where the recessive gives the recessive trait, and because males only have one X, they're either one or the other. So you're going to do some crosses and make sure you include the X's and the Y's. And then the second page, you're doing the same thing with hemophilia. And the third page, you're doing 3 examples of blood type Punnett squares and answering some questions about blood type. All right. So I know there's only 5 minutes left. I'm sorry, I went a little long. I think it was because of all of our shenanigans at the beginning of class. But if you have any questions, if you want